Good morning. Welcome to episode number 29 of the ZOOMTOWN experiment. At this point, things are moving along a lot more fun-like. We've got motion with the Zoomie, and we're into the MicroPython code. For today's episode, we're going to work on getting the Zoomie to move in a straight line without using the photoreflective sensors. We're going to utilize the Rotary encoders that are on each wheel to provide us with feedback of both position and velocity. With that information, we should be able to get the Zoomie to go in a much more straight line. Let's first take a look at some of the rules that I'm following to get the Zoomie to move in a straight line. Rule number one for us is that if both wheels are the same size and both wheels are rotating at the same speed, the Zoomie will move in a straight line. Well, theoretically, both motors should be rotating at the same speed. They're both provided the same PWM signal. They got the same gearing, the same windings, etc., even the same voltage. So it's presumed that they will both rotate at the same RPM. The wheels were all produced one right after the other off the same 3D printer, so theoretically the wheels should be both the same diameter. Perfectly. Well, as perfect as a 3D printer can do. I can assure you they are not perfectly round though. Rule number two, the Zoomie will continue on the current heading, whatever that was at the start of the motion. Well, there is nothing to guide it to turn using the encoder feedback. All we're doing is trying to balance out the data from the left encoder and the right encoder so that they are the same, or if we're actually in a turn, we want them to be at exact ratio to each other. So with this particular exercise, we're only focusing on going in a straight line at whatever heading that the Zoomie will be pointed in at the start of the motion. Rule number three, I think we used to call it Murphy's Law. Everything imaginable will work against rules number 1 and 2. As you can imagine, there's many other outside influences that can cause the Zoomie to deviate from a perfectly straight line. All we can do is deal with the things that are within our control. To achieve that, rule number 4, adjustments must be made to the velocity of each motor as frequently as possible. As you can imagine, if my motion is going to take 3 seconds and I only update it once every second, I've only got 3 chances to try to keep this thing moving in a straight line. Now, as we've been talking all along on this project, we've got our main cycle loop, our deterministic loop, right now is restricted to 5 milliseconds. So every 5 milliseconds, I'm trying to do everything that we need to do. And this adjustment is already built into our system. So we'll be working at a 5 millisecond frequency. That's pretty fast, and we should be able to stay ahead of any adjustments that need to be made. Rule number 5, the adjustments being made have to be at a rate greater than the errors experienced, or the error magnitude will continually increase. This leads to 2 different discussions, but the first one to understand, let's say my deviation is 10, just 10. Forget what units, just 10. But I'm only adjusting by 1. Well, as it's moving away at a magnitude or an error of 10, and I'm adjusting by just 1, it's going to keep going further and further off course, and I'll never catch up and get it back on course. So there's a very important relationship between what error we're measuring and the ratio in which we make an adjustment to correct that error. And that'll take us into rule number 6. If the unit of error is not equal to the unit of adjustment, a ratio or proportional calculation is needed. You'll notice that I use the word proportional, and right away, if you've been into programming or control systems for any given period of time, your mind immediately went to a PID control, and that is pretty much the standard go-to for corrections within a processing loop. Now, in our case, I always start with anything motion control, I start with proportional. And what that does is that I'm going to take the error amount, which oftentimes may be in a completely different unit. It could be in a unit of time, distance, speed, velocity, pressure, and then I'm going to take that data and have to probably create a proportional amount of adjustment for a PWM signal or whatever the case may be to make an adjustment to that error. That's where proportional comes from. We know that the error is going to be something, but not directly related to the same unit of measure as the error. So with this, I start with proportional, but I don't really need to go to integral or derivative. Oftentimes you can get away with just proportional. So I will always, especially in the case of a microcontroller or any device where time is of the essence, I will do my darndest to try to tune just the proportional. And actually I get away with it in many, many cases. We're going to be trying that here. Now, how we implement that, actually a lot of everything we need already exists in our code framework. So we'll start diving into that now. But just before that, let's take a look at what our problem is so that we can come up with an understanding of how severe it is before we try to control it. Over here at Test Track Z for our ZOOMTOWN, I've got a very small layout. This particular one just has some lines on it with some corners in it. And it really wasn't even originally designed for the purpose of a test track for this application. I was actually working on another robotic device and developed this, and well, it's going to serve me well for this purpose here in the ZOOMTOWN experiment. The size of this layout is a total of 48 inches from end to end, which is 1.2 meters, and it's 24 inches from bottom to top, which would of course be 0.6 meters. Now for our testing today, we're only going to be moving from here to about here, and that'll be 34 inches. Our need and our desire for straight line driving off of encoders really only needs to be about 6, maybe 8 inches. I don't need to go this far. In all other cases where we're doing long distance driving in a straight line, we'll be using line following. But I do want to try to get this as close as I can to being accurate. Well, let's take a quick runs down the track and see what we get. Ooh, almost fell off the end of the world there. Now we're going to, because it came off, our error amount that we see on our control or on our on the Thani screen was very minimal, only 20 thousandths of an inch or a half a millimeter. But unfortunately, that isn't going to help us at all. So we're going to clear that guy, and I'm going to run it again. This time, hopefully, I'll have it aimed a little better. Remember, I'm not following any line. Whatever angle it's pointed at, it's going to continue in until it stops. Now our error is showing 0.136 inches. So that's millimeters, probably in the neighborhood of 3 millimeters, 3.5 millimeters of deviation or error in this whole trip of 34 inches. That ain't bad. We'll do another run on it. It does seem to want to go right. Well, we're going to have to scratch that test. I'm guessing that one was pretty bad. We'll clear it and run another test. Now I do have to be careful. I do have a USB cord connected to it, and if that gets caught on anything, it will definitely change directions. Okay, back to our results, and we've got an error of 0.113, so that's around 3-4 millimeters as well. So this is pretty consistent, and most likely what's really happening here is that one of the two motors is running slightly slower than the other, and that's to be expected. It's just, these are really cheap motors and really cheap gearboxes, really cheap wheels, etc. So you're going to naturally experience these sorts of problems. So now let's work on a solution. Our problem, in my perspective at this point, is very minimal. If I slowed this way down to the point where where both motors are barely rotating at a really slow velocity, this thing would be wandering all over the place. But in our case, it's running at 7 inches per second, and frankly, that's a pretty good average speed, I think, for what we're trying to do. So now let's look at the code. I had mentioned that most of what we need to control this is already built into the whole framework. And what I'm looking for, we're in the velocity control section, and we've covered all this last week or in previous episodes. Coming down into the code here, I've got a proportional here that is for this part of the code. That isn't what we want to work on right now, because if you look at this conditional, it says if line following status is equal to true. We're not doing line following at this point, but we are doing encoder feedback to help with maintaining course or heading or turn ratio. This area here sets up some of the initial calculations and information. This isn't really what I want to focus on today. I don't want to worry about turning. All I want to do, well, just so you're aware, if turning is left or turning is right, we're going to take into account some corrective action. But right here is where we're working, or what's happening at this point. We are trying to go straight, or we could be making a pivot turn, meaning that both wheels would be going at the same velocity, but potentially or probably in different directions for a pivot turn. I've added a variable here called ES_proportional. Let's call that encoder steering proportional. We're going to calculate our velocities based on the error, or I should say based on our left and right run velocities as dictated by these previous commands. We're then going to subtract or add a calculation based off of the error amount. Well, where is that error? We'll go up, and we'll see that right here. In this part of the code, we're going to first take care of any backlash concerns. Backlash in the gearing always rears its ugly head in motion control. So this is just to make sure we've at least moved 0.1 millimeters, little over 0.1 millimeters, or 0.005 of an inch. From that, if we're making a left turn or a right turn, we would be working with an error based on the turn ratio and the current position where it should be. In our case right now, we're looking at straight line driving, so our error is the left position minus the right position. That's it, just strictly how much I'm off course. From that data, we're going to assign our run velocity into left and right. I'm going to skip down past this, and now we're looking in this area again. So now let's look at our left run velocity is equal to left run velocity minus the proportional, our positional error times the proportional, which right now is set to 1. Same thing for right. In the case of the right wheel, we're going to increase it by the amount of proportional against the error. Now, you'll have noticed we're dealing with velocity here, which is in inches per second, and here we're dealing with error, which is within, or expressed essentially in a very small amount of inches. Frankly, we're in the decimal point of inches down to 3 decimal places, or 1/1000th of an inch. A couple of microns if you're in the metric system. So this is our proportional adjustment. From this, we are going to make a couple of checks because the system doesn't like running at too low of a velocity or too high of a velocity, if they're over 0 or under 0, depending on how you're looking at it. So if left run or right run is less than 0 inches per second, we've got to make it at least equal to 0. Anything less, and the math gets goofy further down the road. Now we'll set the velocity up here. That is in this area. We went through all this last week. Just real quickly, what we're going to do in here is calculate our duty cycles and then also account for maximum allowable settings and minimal allowable settings for that duty cycle. And then finally here, we'll call this function which sets the duty cycle of the motor. So by adjusting, where did he go? All the way back down here again. By adjusting this encoder steering proportional value, we can increase the amount of velocity change based on the amount of error. Proportional. The one is proportional to the other. Now, if you were looking at the code earlier or last week or the week before, you probably saw the magic number where I settled in on the last time. Now, what we're going to do, we'll just kind of work our way up. We already know we're getting about 0.12 inches of error at the end of a 34-inch move. Now let's take this up to, say, 5 and see if it gets any better. And in truth, any PID tuning is trial and error. There are some rocket scientist types that can actually calculate a lot of this right, really, really close. But even within industrial environments, PID tuning is often done by trial and error. So we're going to take that path because I'm certainly not a rocket scientist. So let's take this with our 5 and we'll run down the track and see if things get better or worse. Wow. If we look on our very first pass, our error was cut in half by increasing this to 5. Now at this point, my error between the left wheel and the right wheel over this distance of 34 inches is 60,000ths of an inch or 1.5 millimeters. I frankly want it better than that. So what I'm going to do, I will increase this to, say, 8, which isn't a lot, I think, based on what we're doing here. But let's see what happens. Okay, again, I'm really not worried about heading. Heading has nothing to do with what we're doing. Error does. Now at this point, we're down to 34,000ths of an inch, or a little bit less than a millimeter at this point. So we're still improving. Okay, let's go to 10. See if we keep getting more and more improvement. Actually, on camera, I think if I try to align this by looking at it on camera, I might be able to go more straight or have a better heading, so that doesn't add confusion. Now we've increased to 10 for our proportional. $32. We got a little bit better again. So we will go up to, let's see, let's go to 13, my favorite unlucky number. There we go. Wow. Our error is a negative 1/1000th. Well, if we rounded it up, a negative 2/1000ths of an inch. The thickness of paper is 3/1000ths of an inch. We're getting really, really close. Let's run that test again. We may stop right here. I would say if I'm pretty consistently better than about 10/1000ths of an inch, I'm going to be pretty happy with that. That was 9,000. That one will be 10/1000ths if you rounded it up, or 0.25 millimeters. Let's give it another try here and see what that one is. We might boost this up a little bit more. 7/1000ths of an inch. Okay, I think I'm going to go up a little higher. Let's go to 15. We'll clear out all our data. Now what will probably happen, each one of these Zoomie cars may need to be tuned. I'm not expecting them all to behave exactly the same. Okay, we've got a 4/1000ths error, 0.1 millimeters. And we'll run that a couple times and see if we're pretty much in the ballpark at this point. 6/1000ths of an inch, 0.2 millimeter. And 3/1000ths. I'm pretty confident we've got this dialed in really, really close. Now we're on the test track at this point. When we actually start driving around in the ZOOMTOWN experiment, the surfaces are different. There's other influences, and that could affect it more. But right now, with that level of accuracy over this amount of distance, I'm pretty happy with the results. I certainly don't need to go into adding integral or derivative controls with the PID loop. At this point, proportional is doing exactly what I need it to do. Next week, we're going to be taking a look at line following and the steering. So that'll get a little bit different, but you'll find that whether we're using line following or we're using the encoder feedback, the control system loop or the control loop system is pretty much the same. So with that, we'll wrap up this episode right now, and I look forward to seeing you next week.